Now we're going to talk about something called neural style transfer. So this is a different use really of neural networks. The idea is we're trying to do something creative. Let me show you what I am talking about. So what's going to happen is we're going to take an image. In this case, this is a content image. Okay. So we're going to take an image and we're going to try and be creative with it, in the sense that we are going to take a style image. So this is a style image. And what we want to do is create a new picture which has the content of this content image, but in the style of the Van Gogh. So we'll take this one and we will sort of add it to this one. Okay, so the content from here, you know, the buildings, the river, and so on, and then in this style. And so we can end up with something like this. So you can see here, we have the buildings, but we have the style of the Starry Night, Van Gogh, right? We've got, it's like curvy a little bit, there's swirls, right? The swirls here, the colors are the same. And so this is what I'm going to call my combination. And we actually want to be able to do this for any content image and any style image. So to extract somehow the style from any image, extract the content from the image, and then produce this combination image. So that is our goal. Clearly, how are we going to decide whether we succeeded or not? It's going to be based on how this looks, right? We look at this and we say, yes, we as humans seem to realize this kind of does look like the same kind of content and does look like the same kind of style. So we're not going to be doing any labeling or anything like that. Really, the approach we're going to be using is different from anything that we've seen so far. So we're going to talk about our content image and look at what it means to extract the content from that. So here's what we're going to do. We're going to take a VGG neural net, pre-trained. Okay, so this is a big neural network. And of course, if we fed this content into this neural network, we would get out one of, 1,000 different categories, because this was pre-trained on ImageNet. So this has convolutions. If we look at the neural network, it's broken really down into convolutions, and then some fully connected layers. And then at the very end, a softmax. We actually don't care about the fully connected layers and the softmax. We're going to be focusing on the convolutional part of this neural network. So we're going to use gradient descent in order to solve our problem, but we're going to use it in a way we haven't used before. And that is, instead of feeding something into our neural network and then using gradient descent to update the weights, we're going to instead feed in something different. So we're going to feed in a combination image. In this combination image, to begin with, we are going to set to just random values. Very similar to the way if we have an uninitialized neural network, we set the weights and biases to random values. Okay? So this is going to be initialized randomly. And what we're going to do then is feed this into our neural network. So let's just ignore the content right now. We'll feed this combination into our neural network. And then what we're going to do when we get done is we're going to have a loss function. And that loss function is going to somehow measure the fact that we have a content image and a style image, and that this is going to be some reflection of those. That's really a lot of where the magic of this is going to happen. We have our content image, we have a combination image, and of course we also have a style image. So we're going to feed this through the network, and then we are going to use a loss. Okay? And this loss is going to measure how far away is this combination image from a good combination. How are we going to measure that? Right? So we're going to say basically the loss of the, I'm going to call it ICOMB. Right? So that's the image, that's the combination image. Well, how can we do this? Well, I know. Let's go ahead and compute two different losses. A content loss of the combination image plus a loss for the style. Well, I mean, okay, we still have no idea how to do this, but that's okay. So we're going to just say the loss overall of the combination is the loss of the content plus the loss of the style, and we probably need to have some sort of a scaling factor here, right? Some beta, and maybe 1 minus beta, or just a beta here should be enough, right? So we can scale these so that they are roughly in the same range, right? It's possible if our measurement of the loss of the content might be in one range. This might be in, let's say, units of in the hundreds, and the loss in the style might be in thousandths. Well, then the content loss would dominate this overall. So we do this to just kind of scale these so they're in the same range. Now, this is really just push the problem down to say, okay, how do we figure out the content loss and the style loss? And clearly there'll be some measurement in the content with the original content image, right? So this is, we're going to say I sub content. That's the image, right? This is the, whatever size this is with R, G, and B. So this is a depth of 3. This is a depth of 3, the style. And we again have our I style. Okay? So that's what these images are. I style, I content, and I combination. This guy gets initialized randomly. But if we could figure out, right, let's say we could figure out this loss and measure it, then it's a simple matter. We can just take the loss, which presumably is going to be some function of something about what's coming out of this neural network or being calculated in the neural network, and then we can calculate gradient descent. We'll calculate gradient descent, not the partial derivative of the loss with respect to any weights in here. Instead, we're going to actually calculate the partial derivative of the loss, right, the combination loss, this loss, with ICOMB pixels. That is the pixels within here. So what is the partial derivative of the loss with respect to this pixel and this pixel and this pixel and all these pixels? And then we can go ahead and update to make them slightly closer to reduce this loss. And so we'll just be using gradient descent to improve this combination image. That's the plan. Now, how are we going to do that? Well, we've actually got to go in and look at how do we do these two content losses. If we could figure out a way to measure a content loss and a style loss, then I think we're done, right? Because the process is just the same process that we normally use, right? We would basically initialize ICOMB randomly, right? And then we would, for E in range of epochs, right? What are we going to do on each epoch? So we'll go ahead and calculate the loss of ICOMB. Presumably that's going to use our neural network here. I'm giving you a hint ahead of time, it is. And then we will go ahead and calculate the partial derivative of the loss with respect to ICOMB, and then update ICOMB minus equals lambda times the derivative. So this is going to be our process that we are going to use to iteratively improve ICOMB. And we could replace this line here with our favorite optimizer. This is a simple stochastic gradient descent. We could also use more complicated optimizers like Atom or anything else. So let's keep this in mind. The only complication is basically how do we calculate the loss? Once we calculate the loss, we know how to calculate the partial derivatives, we know how to use an optimizer to update ICOM, we're familiar with going through epochs and so on. So that's the job, figure out those losses.